Alright, this is Thursday, May, what is this? May 20, 20, 20, 20, 21, 22, 23, May 23rd. So, we're going to cover four problems. We're going to cover problem 18 first, and then before I cover problem 18, some of you were asking which problems on the problem set are worthy of you looking at again, maybe a second time right before the test. Make sure you know how to do them. They are 6, 13, 17, 27, 35, 42, 43, and 44. That doesn't mean the other ones aren't worthy of you looking at a second time, but those are the ones that I saw. Anyway, I will have this video up on YouTube, so if you want to search for it and pick those up on YouTube, that's totally cool with me. So we're going to go and get started. I'm going to move through problem number 18 first. Just another announcement. I'm certain that all of you have your problem sets right now. Make sure at the end of the period you turn your problem sets in back to the substitute, whoever it may be, and then that's it. Okay, so this is the only time you're going to have those available. And don't forget to turn it back into the substitute. That's your responsibility to get it to him or her. And then I will be here tomorrow, basically 7:30. If you need some quick help, that's fine. And then most of us will be taking the test on Friday. So there it is, and there it is. So here's number 18. It says, determine the force exerted by the bicep muscle, assuming that the hand is holding a ball with a mass of 5 kilograms. Assume that the mass of the forearm is 8.5 kilograms with its center of mass located 20 centimeters away from the elbow joint. And then assume that the center of the mass of the ball in the hand is 30 centimeters away from the elbow joint. The arm is held at a 90-degree angle, and the muscle contracts, or the muscle contact is 4 centimeters from the elbow joint. So I guess a diagram is going to be kind of important for us to kind of get started. And obviously this is my wonderful diagrams that you guys love. So here is the pivot point. This is going to be your elbow, and then we'll have the muscle come down and connect here. So the muscle is going to be pulling up on your arm. We'll have the center of mass, I'll do CM, right here of your arm, and then here's the mass that will be hanging, or you'll be holding on to in your hand. Some distances real quick. This is 4 centimeters. This here is going to be 20 centimeters, and all the way out to this guy out here is going to be 30 centimeters. Alright, so I think what we want to do is what are we ultimately looking for? I think we're looking for the force that the muscle pulls up on the arm, and I think I need some other numbers here. I think this is going to be 8.5 kilograms. That's the mass of your arm, and then the mass of the object that's sitting in your hands is 5 kilograms as well. Alright, so hopefully you recognize this by now, that as this is a teeter-totter problem, and when we do teeter-totter problems, I'm going to kind of slide this sideways and blow this out a little bit. We need to go ahead and set it up technically as something that looks like this. Now, if this is in equilibrium, where everything cancels out, then I can say that the alpha here is 0, and then we have 0 on the right hand side. Okay, so this part of the equation is asking for you to list all the torques that are going to be acting. Well, I've got 3 of them. I've got one exerted by the bicep, one exerted by just the mass of the arm, and another exerted by the mass of the ball in the guy's hand. And so I'm going to go ahead and figure out whether they're clockwise or counterclockwise. So the force is pulling up, so that's going to be, that'll be counterclockwise. I had to think about that, which is positive. Remember that for the test. The center of mass is going to be pulling down, so that's going to be clockwise, which is negative. And then the mass of the ball sitting out here is going to be negative as well, and that's that would be clockwise. So I got 3 of them, and I'm going to go ahead and plug them into my equations. So I've got the torque exerted by the bicep muscle minus the torque exerted by the center of mass minus the torque exerted by the mass that's in the hand of the person. I'm going to scooch down a little bit so I have some place to write. So this is going to be the radial arm of the ball times the force exerted by the ball. Radial arm of the bicep muscle times the force exerted by the bicep muscle minus the radial arm of the center of mass times the force exerted by the center of mass minus the radial arm of the ball that's in the hand times the force exerted by the ball or the mass that's in the guy's hand. That's going to equal 0. Now we're ultimately looking for this guy. So this force, though, is a weight, and that's equal to mg. And so I'm going to go ahead and do those substitutions first. So this is going to be the radial arm of the ball times the force of the ball. I keep saying that, of the bicep muscle minus the radial arm of the center of mass times the mass of the center of mass times the acceleration of gravity minus the radial arm of the mass in the hand times the mass of that mass times g equals 0. Okay, I'm going to solve for this guy, and when I solve for this guy, I'm going to take this chunk and move him to the other side. I'm going to take this chunk and move him to the other side. And then at the end, solve for this guy. So I'll have the force exerted by the bicep muscle. Move this guy over first, so that'll be RCM MCM G plus RM MM G all divided by RB. And then once we're here, it's just a matter of substitute numbers. So I'll go ahead and plug these in. So the radial arm of the center of mass. So let's go back to the diagram and look at this real quick. The radial arm is always drawn from the fulcrum. So here's your fulcrum, and here's the center of mass of the arm. So it's going to be this distance here, and that's going to be 20 centimeters. So I'll go ahead and plug in 20 centimeters here. And actually, since I'm dealing with a force which has newtons, it's probably best that I use meters. So I'm going to go ahead and substitute that in. So this is going to be 0.2 meters. Okay, times the mass of the arm, and that was 8.5 kilograms, plus the radial arm of the ball. So if I go over here, radial arm, remember, is always drawn from the axis of rotation to the ball, and that distance right here is going to be 30 centimeters. And then the mass of the ball is 5 kilograms times 9.8 meters per second squared. I'm sure you guys are all screaming at the video. I missed this, didn't I? Alright, so let's get all that in there. So I got the radial arm, the mass, G, which is what I just included. And then I've got R, M, and then the other G. And then the other one is the radial arm of the bicep muscle. And that'll be 4 centimeters, so 0.04 meters. Okay, so the rest of this is just a matter of you plugging this in to the calculator, and when you get the answer, we should get roughly 784 newtons. Alright, I think that's it. Hopefully that helps. Okay, the next one that we're going to go ahead and move into is question number 33. So I'm going to slide this off. Question number 33. And I'm just going to go ahead and turn to it on my sheet. Okay, 33 says this: what is the angular momentum of a 2-gram particle moving with an angular speed of 5 radians per second in a horizontal circle of radius 5 centimeters. Alright, let's draw a circle first. So it sounds like I've got an object. What is the angular momentum of a particle? So it says it's a 2-gram particle. So I'll go 2 grams there. with an angular speed. Alright, so what's angular speed? That's omega. So omega is going to be 5 pi radians per second. And then the radius of the circle is going to be 15 centimeters. And then they want the angular momentum. So we have an equation for angular momentum. Really, we just have one, and that's L equals I omega. Alright, now, so we have a particle that's just basically zipping around. So we have to figure out which I equation we're going to use. And if you remember, on the back side of your equation sheet, on the upper left-hand side, you'll notice that there's about 6 I equations for moments of inertia. The first one is a generic one. The rest of them are special equations, like one for a disk, one for a sphere, one for a cylinder, those type of things. Well, we don't have necessarily a special object here. It's just a regular particle. And so we're just going to have to use the first equation, which is sigma mr squared, and then the W. Now, I only have one particle, and it's a certain distance from the axis of rotation. So when I do the sigma r squared, it's going to be pretty simple. It's just going to be mr squared. Now, if there were two objects, like one out here, then I'd have to do mr squared plus mr squared. But I don't have that. So the rest is just I think, pretty much plugging them in. So the mass here, let's see, I guess I'm going to try to stick with the regular units, and that's kilograms, meters, and seconds. So mass is going to be, they got 2 grams here, so that's going to be 0.002 kilograms. Make sure I did that right. Yeah, 1, 2, 3. That's correct. Times the radial arm, and that's the 15, so that's 0.15 meters. I have to square that. And then times its angular speed, and its angular speed is up here at the top. And that's 5 pi radians per second. And just as a rule of thumb, we talked about this yesterday, if in doubt, just go ahead and switch everything to radians, and 9 times out of 10 you'll be right on the money. And so then it's just a matter of plugging stuff in. Just don't forget to square the 0.15 meters when you do that. And when you do it, it'll be 7 times 10 to the negative 4th kilogram meter squared over seconds. And there it is. That's number 33. The third one you asked for on the board was number 35. I'm just going to get a little more room here. And here's 35. Alright, so 35 says a person opens a door by applying a 15 Newton force perpendicular to it at a distance of 0.9 meters from the hinges. The door is pushed wide open to 120 degrees in 20 seconds. Alright, so let's draw a diagram. So it sounds like we've got a door. So there's my fancy door. And I'm pushing on the door, so we'll go ahead and exert a force on the door. And that force, they say, is 15 newtons. So all I'm doing is basically read the problem and just trying to draw a picture from what they have. They tell me that the distance from the hinge to the force is 0.9 meters. So this distance is right there. And this door, when it opens up, is going to open up 120 degrees. And the time that it takes is going to be 2 seconds. Alright, and they want to know how much work. Well, we've got really 3 equations for it. Let me write those 3 equations down, then we'll talk about them. So we've got F dot D. That's a long time ago. We have work as a change in kinetic energy. And then we have this new one, work is equal to torque times theta. Well, as I kind of look at this, I'm looking at, okay, we have a rotation here, so that's probably going to be theta. I have a radial arm, I've got a force, that's probably torque. Probably we're going to be using this guy. So I can kind of narrow it down from there. So I'm going to go ahead and rewrite this on the side a little bit. So I've got work is equal to torque times theta. And then I need to go ahead and figure out what that torque is. Well, the torque equation is going to be R cross F times theta. Remember that R cross F is R F sine theta, and all of that's going to be multiplied times the theta on the outside. So I have 2 thetas, but keep in mind those two thetas are actually different, and we'll help you see the difference between them in just a second. Alright, I think I have enough information that I can go ahead and plug in numbers. So my radial arm, R, is always drawn, remember, from the hinge to the point of contact of the force. And so there's my radial arm right there, and that's going to be 0.9. So I'll come over here. So that's 0.9 meters times the force. There's the force is 15 meters. Sine of. Alright, now the sine of business, it's sometimes kind of tough to figure out where this comes from. I usually just work the equation backwards. This theta came from r cross f. So this piece came down here. So that theta is the angle between the r and the f. And the angle between the r and f, here's your r, and there's your f. And so the angle between them is going to be 90 degrees. So when I come over here, I'm going to go 90 like that, close off that big parenthesis, and then times theta. This theta comes from up here, which is going to be how far the door rotates, or at what angle the door rotates. And that's the 120 degrees. So I need to be careful, though, when I plug in 120 degrees. This can be kind of confusing. This angle here actually needs to be in radians. This angle, it doesn't really matter what it's in. You can actually have it in degrees. You just need to have your calculator set for degrees because you're going to be taking the sine of it. If you had it in radians, then you just have to have your calculator in radian mode when you're doing the sine. But we need to convert this. So I know that, what's that going to be? That's 180 degrees is pi radians. And so my degrees will cancel out, and I'll be left with radians. So if I do 0.9 times 15 times sine of 90, sine of 90, by the way, is going to be 1. And then times 120 times the pi, divide by 180, I should be in business. I'll do that one more time. 0.9 times 15 times 120 times pi, all divided by 180. And that should work out for me real well. So here it is. I think if I do it, you can double check on the calculator here. It should be 28.26 joules. Now, part B asks for the power delivered. And the power, we're just going to reach back and grab this equation here. And that's the power equation, which is the amount of work that I do, which is this guy, and how long it takes me. So we have 28.26 seconds. I'm sorry, 28.26 joules divided by the time, which is 2 seconds, and then that gives me 14.13, and it's not going to be measured in joules. 14.13 watts, and there it is. Hopefully that helps. That's number 35. The last one that you all asked for on the board is number 38, and so I'll run through that one for you. Let me scooch the paper down a little bit, and here is number 38. Alright, number 38 says to start her lawnmower, Julie pulls on a cord that's wrapped around a pulley. And I'm just going to go ahead and just kind of draw this out as we do it. So here's more or less a pulley, okay, and Julie's going to pull with a force here, so we'll kind of go Julie here, on a cord that's wrapped around a pulley. The pulley has a moment of inertia about its central axis, so they're going to give us the moment of inertia. That's nice of them, so we don't have to look it up off the equation sheet. It's going to be I equals 0.550 kilogram meters squared, and then they give us the radius, and so R is going to be 5 centimeters. And then they throw in a kind of more or less a curveball on this, and it says there's an equivalent frictional torque impeding her pull of the pull that she's exerting, and that torque that's exerted by friction is equal to 0.43 meter newtons. So I really have two torques here. I've got a torque that Julie's using to speed it up, and then I have a torque of friction that's causing it to slow down, and they're almost playing tug of war. And I'll go ahead, I have to play with that a little bit. And so the question is asking to accelerate the pulley at an acceleration, so let me write that down. So they give us an acceleration here of 4.55 radians per second squared. How much torque does Julie need to apply to the pulley? And so let's go ahead and run through this. We're looking for force. And the force that I'm going to use, or the equation that kind of govern my thinking, is the torque equation. And the reason I'm going to use this one is because they gave me alpha, and they gave me I, and then they gave me some torque. So this equation kind of comprises most of what I need. So I have sigma F, and I need to go ahead and remember that there's actually two torques here. There's a torque that's exerted by Julie, and then a torque exerted by friction. Now, from the problem, they don't tell me which one's clockwise, which one's counterclockwise. But I do know that one is going to cause it to speed up and one is going to cause it to slow down. And so they are playing a tug of war. So the most important thing is that I make one positive and one negative. They just need to be opposite signs. Alright, so I'm going to go ahead and substitute equations. And let's see here, let me think. So we're actually looking for this guy right here. So the torque exerted by Julie. So all I have to do is just move this guy to the other side. So the torque exerted by Julie is equal to I alpha plus the torque exerted by friction. And then I think I have everything I need. I have I, they gave me that earlier. That's 0.55 kilogram meters squared times the acceleration of it, and that's 4.55. That'll be radians per second squared, and that's a nice thing that they actually gave it to us in radians. We don't have to do the conversion, because remember, we want to have radians when we're plugging this stuff in, plus the torque exerted by friction, which is 0.43 meter newtons. And if you plug all that in to your calculator, you should get 2.93 meter newtons. And there it is. That's all you asked for, so that's all you get. It's about 22-minute video. You can use the rest of the hour to work together to work through this, and then make sure before you leave you turn all your problem sets and multiple choice into the sub before you take off. And then and keep in mind, I won't have them graded Friday morning, so because I'll be driving through the night to get here tomorrow morning. So so I won't have them graded, but you're more than welcome to come in and ask me questions at 7:30. Have a great day. Bye.